Hey, great. Thank you for coming to the F# talk at Lambda Jam. We're talking about computation expressions today. They're a feature of F# that is seen as sort of an advanced feature of F#. So I'm going to spend the first half of the talk talking about how simple they are, and in the last half showing some real-world examples of the sorts of things it enables, which are really interesting. So anyone who's done some F# will have seen things like sequence expressions. For the .NET developers, it's just a synonym for basically IEnumerable. And so what we've got here is we've got our sequence block, and we're yielding 1, 2, and 3. So 1 is just being yielded directly, and then the yield exclamation mark is allowing us to yield a subsequence, and it basically gets flattened out. So that's a built-in construct to F#, but it's also an example of a computation expression. The other computation expression that comes with F# is it's the way that it composes asynchronous computations. So in this case, I've got an async block. That fetch async function, if I mouse over it, takes the URL and returns an async of string. But you can see I've got a let exclamation mark. So exclamation mark is your clue that something interesting is going on. And so on the left-hand side, the HTML that comes back is not async of string, but a string that I can work with directly. So you can see on line 6 there, I've just been able to print out the length of the string. And under the covers, it's transformed that code into something that is doing non-blocking calls out over the network. But we can write sort of imperative style code in that block. We can think about things in the order in which we want to think about them, in the order in which, not in the order in which they happen. So there's no callbacks and things here explicitly. But rather than build these into the language directly, what the F# compiler does is allows us to build our own blocks like this. So as a way of giving you a simple example, F#, like most languages, has an option type, which represents you've either got some value or you're missing a value. So what I've done here is I've built a maybe computation expression that allows us to thread through the failure case into our code. So lookup name and lookup age could both fail or return none. But I haven't dealt with those explicitly here, but the behavior of this code is that if either the lookup for name or the lookup for age fails, then the whole expression will just return none. And so you can see I've got my let exclamation mark there, and I'm inside the maybe block. So what the compiler does for me is it transforms my code into something that looks like this. It's taken maybe and called the bind method on it for each of the let expressions. The first argument to the bind method is just the right-hand side of the let exclamation mark expression. And the rest of it is a callback that represents the remainder of the computation expression block. So it's taken away nesting all of those callbacks for me. You can see age is actually nested. That's a second bind call there on line 3. And it's nested inside the bind call for name. But the compiler's done all of that nesting for me. So I started with nice simple code like this, and it's turned those into bind calls. And the last innermost call is just a call to return. And I haven't had to worry about that directly as the end developer. So what's maybe? Maybe is simply a value that maps to an object. I've called it maybe builder, that just has those two methods on it. So return does the obvious thing. It takes a value and wraps it up in a sum. And bind takes the input. If there's no value on the input, then it just returns none. So to basically short circuit out of the computation. If there is some value, then it applies the function, which was the second argument, or the continuation for the rest of the computation expression, and returns that. And so those of you who are familiar with do syntax from Haskell or for expressions from Scala will be already familiar with sort of how this is put together. It's a very similar thing. And we've got obviously the normal suspects, bind and return. There's actually a whole bunch of different transformations that the F# compiler will do. So you saw back for the sequence expressions, it supports the yield keyword. that simply gets transformed into a call to yield. Yield exclamation mark, which was used in the sequence example to return sub-expressions, it works in exactly the same way. So what you do with those differences in syntax is up to you as the person building the builder for the computation expression. And in fact, return and return exclamation mark are exactly the same as yield and yield exclamation mark. They just give you an opportunity to do something with the value. So often when you're working with bind, you'll use return, and when you're working with something that looks more like a sequence, you'll use yield, but it's just aesthetics basically. You can also use it within like if-else statements and things like that. And so in this case, all it does is it takes the foo, which is pointed to our computation expression builder, and turns the body of the if and the else statements into calls to whatever the appropriate computation expression is. So that could have been any kind of computation expression code in there, but in this case it's just return, so it just transforms both those bodies. Computation expressions offer a zero method. So if you implement a zero method, what it allows you to do is leave off the else block on your if statement, and the compiler will just fill in a call to zero. So for instance, in a sequence example, if you wanted to optionally yield something, it'll just fill that in with a call to zero, which would presumably yield nothing. And you can leave off the if block. F# being a sort of a hybrid language and fitting in with the .NET framework needs to support things like resource disposal in a similar way to the way C# does it. So basically it transforms a use call. So normally an integer wouldn't need to be disposed. In this example it is. Into basically a call that separates out the value you've got from, once again, the continuation. And they've got to use exclamation mark for when you want to combine something that needs to be disposed with the normal bind operation. So there's no extra call here. It basically just wraps, sorry, there is an extra call, there's no extra method here. But basically the outer thing is the bind operation. And then inside of that, it'll have a continuation that then calls the using method. Do is included. So do is just a special case of let, where the return type is unit. I only included this slide here to explain the joke in the talk's title. You can return multiple things and yield multiple things. And in that case, you need to have a combine method on your builder. So you'll see here I've got also a delay. F# is a strict language by default. What this allows is for, it basically wraps your code in a unit to the value. So where Ed was talking in the keynote yesterday about unit to a value is not very interesting. In F# it actually adds basically delayed computation to our expression. So you can see here the return 1 is the first argument to the combine call, and then the second one is actually a delayed version of return 2, so that it's not confused eagerly. 4 expressions are supported, and it's just basically a map call. So you've got the iterator passed as the first argument, and the body of the 4 expression passed as the second. And while is similar, the check is passed as the first argument, and the body is the second. Try finally is supported, so this is resource cleanup again. And try with allows you to pattern match on exception types. So this is not all of the options, but you can start to see that it follows a very similar pattern. It's basically what it's doing is taking code inside the computation expression and basically just composing functions for you. So something I haven't mentioned here at all is types. And that's because all of this happens before type checking. So the compiler basically just does a syntactic transformation, and it's up to you then to make sure that the transform code compiles. So normally we would have an intuition that, say, bind is the wrapper type and then a function from the underlying value to the wrapper type to the result of that. But bind can actually have, for those 2 arguments, any type you like, so long as after transformation it compiles. This allows you to do some sort of interesting things with it. I'm going to give an example at the moment of asynchronous sequences where we've got different types for bind from some of the other operators. So you get a little bit of flexibility in the way you're able to compose these things. And the main thing is you want to have an underlying data structure that composes well, so like a monadic structure or something like that. But you've got a little bit of freedom to play with there because the only thing that is required of you is that it compiles. So you can either delight your users or confuse and upset them, depending on how you set those types up. So have I been clear enough about really all it is a syntactic transformation? Has everyone sort of got what the computation expressions are? No questions at this point? Awesome. So now I'd like to show a little bit of an example of where they actually add a lot of power and utility. So there's a library for F# called Asynchronous Sequences. And in this example, I'm going to use it to sort of work with a data source that's paged. So this comes up a lot when you're accessing a database. You want to go and get a page of data at a time, or you're calling a web service. And the data source effectively looks like this. You get a page of data. Maybe it's skip and take or something like that. And the result is it's an async call. It's going to be a network call. And it's going to return some sequence of values, which is not the whole result set, but just one page of it. So if we wanted to work with this using the things I've sort of already shown, sequences are lazy sequences. This would be one implementation. Start reading from the bottom. We loop from page 0. We go through. We'll grab a set of results. We yield those results. And while the last page wasn't empty, we go and grab the next page. The issue there is obviously on line 5, where we've done a dirty great synchronous call in the middle of our sequence expression. So we've lost any ability to sort of push that async part of it up and into our calling method. We're just going to do a dirty great blocking call in the middle of our code. We could reverse this and take it from the async outwards. So in this case, what I'm doing is I'm doing a loop inside of an async block. I grab my results on line 3 there, which is fine. And then I've got an accumulator. So basically I do the call to grab the next page, and I'm appending that to the sequence. And then once I get a page that's empty, I return the accumulated value. Obviously the issue here is that I've gone and grabbed all of the data from all of the pages before I've had a chance to do any sort of transformation on it. So we could smarten this up and put a limit on how many pages we get or something, but we sort of lost all that compositionality in this case. So what we want to work with is a structure a little bit like this, where you can see I've got async seq, where our structure is basically we've got an async, and then we've either got nil, which is the end of the list, or cons, which is a value, and then the next part of the asynchronous sequence. So that at each step when we're returning a value, we've got a chance to do an async call as well. But we probably don't want to work with that directly. So here I've built a builder. These are the base methods I've defined, and this is mostly from the library. There's a few more, like 4, that are supported, but they're built in terms of these. So singleton obviously just yields a value, basically just wraps it up in the async seq. I've got a yield from call. Because F# supports method overloading, I've got 2 yield from implementations, and the compiler will just work out which one to call. Yes, Len? Oh, sorry, the builder is just the object behind the value, sorry. So maybe is the name of the computation expression. It's the value that all of those calls get mapped to. The builder is just the implementation of that object. But yes. But there's nothing special about the name builder. Basically, it's just that it will call methods on whatever object that is. Yeah, so method overloads maybe aren't always a good idea. It saved me some space on the next slide, so I've done an override so I can just yield exclamation mark a sequence or an async sequence. Bind, you'll see here, is just referring to the normal async.bind. So what that means is that inside of our asynchronous sequence computation expression, I can use the let syntax to just make an async call directly. And delay and zero are very straightforward. So what this enables is code like this, where now I've got my let exclamation mark. I'm getting my results, which to me is just a sequence of integers. I'm yielding those directly. And then, so between let and yield, it'll have done a combine call. And so basically, I'm able to then check whether the page is empty and loop back around. So it, with the help of the builder, has been able to build up that sort of data structure for me in very simple, straightforward code. And because that underlying data structure is quite composable, I can then use get all results from the previous slide and do things like loop over those results and transform them into, say, a string, as I've done there. So I'm able to sort of compose these things together without losing any of the laziness or the asynchrony of the code. And we can also then build higher level functions in terms of our async seek computation expression. So here I've got a filter that basically just loops over the results, makes a check to see whether it should be included, and then optionally yields it. And so you can see there the simplicity of the code there where the else block is missing, but it will just return async seek.empty in that case. So hopefully that shows that you can get some quite nice code out of transformations that the compiler is helping you with. So last year, so this year Ken's been talking about category theory. Last year I did a wonderful talk on free monads, which I thought was really practical and I could take back and use straight away. So at the time I was working with an event store database and testing it and testing all of the failure cases for things like versioning of data was a bit of a pain. So what you can see here, and this is not exactly what we had, but this is a simplified version, is a key value computation expression. And in my little domain-specific language that I've made here, we've got the call to read value, which just takes a key and returns either, if the data exists, then it'll have a version and a current value. And if it doesn't, then it'll just have a none. So the two keywords that are in my language here are or read value and write value. And what this is producing under the covers is expressions in my sort of free monad language. So don't worry too much about the details here. If you wanted the details, you should have come last year. But basically, it takes the inputs to the functions, and what you get there is a continuation which takes the results of the function and will produce a continuation for what the rest of the code is. So that's going to line up reasonably well with our let calls. And what we've done by writing our program in this language is that we've separated out the implementation or how we're actually going to run it from the specification of the program. So this is all pure code, and we can then write an interpreter for that data structure that will actually run it. So again, don't worry too much about the details here, but at a high level what's happening is, this is my unit test version of my interpreter. So I get my program. This is the object we defined a couple of slides back. In this case, I'm just doing testing, so my data store is just a map. And this one is just going to do one step. So it's going to pattern match on the program. I'm either going to do a read value or a write value, implement those in terms of the map, or pure. Pure means the program's finished and we've got a result. And it's either going to return a continuation, or it's going to say it's complete and return that to the interpreter. So then to run this program, all I do is I call my interpret method, which is basically just a loop that runs that step until the program's complete and then returns. So obviously to achieve that sort of key value computation expression, I need once again a builder. Most of these methods are just the default implementation. So if you go to MSDN, they provided with the language of default implementation once you've got a bind and return. And so in this case, what bind is doing, so just a reminder that's mapping to the let calls or let exclamation mark calls, is basically mapping the rest of the program into that continuation I showed on the data structure. So you've got the fmap call that then looks at what it's got, and then it's mapping through the continuation so that you're composing basically a program full of continuations that the interpreter can then step through and run. And so we get back to this nice example where I've got my key value thing, I can interpret that against an empty map, and you can see I can get back something that I can easily test with that now contains, the value and the return. Not only that, but having used a nice structure like that, I can then compose key value programs. So you can see on line 5 there, I'm calling my original append value method, which is, we mouse over the type, is actually the free key value data structure that we're building. And I've been able to write another key value program that loops over it basically and keeps trying until the operation succeeds. So I'm able to build up programs this way with something reasonably close to normal F# syntax, but it's actually building a DSL that can be interpreted separately. And of course, we're going to have a production interpreter against, iReal data store, because that's how things look. And we're actually able to add back things like async at this point. So for the real interpreter, presumably it's going against some real database. And so at the interpreter level, we're then pattern matching over this pure data structure, wrapping it in async calls so that the end result is an async. But we haven't had to worry about that for our unit tests until we actually get to running against the real data store. And where this starts to get even more powerful is we can write different interpreters. So we had a very simple unit test interpreter that just ran the code against the map. But we can start to do things like interleave multiple programs. So one of the things we were testing with our data store was that we could have multiple workers all going at once, and that certain properties would hold true no matter how many workers were running. So what this code here is doing is it's taking two programs, running against, once again, just our map version of the data store. And what the loop and the run step are doing is running those alternately. There was a great talk yesterday on property-based testing. You could easily imagine that instead of just running one step from one and then one step from the other, you could have the property-based testing thing generate 2 or 3 steps of one step of the other, find those different cases, and test that the properties of your program hold true no matter how many people are running, without having to deal with a real data store or any of those asynchronous concerns. So there's lots more computation expressions. In a lot of cases, people are just wrapping up the same sorts of things that you do with syntax in Haskell. So choice is often a nice one, where you just have a choose block, and rather than just having some or none, like I had, you might have the normal values and then a sort of a failure value. There's an implementation of software transactional memory that uses the computation expression syntax. You're able to sort of get at some of the data as you go through, so things like logging can be done, and you can also build even parsers and things like that. All the sort of standard monadic operations can be built this way. And some other classes of things can be done depending on how you use those keywords. So I think it supports things like monad plus. It doesn't support applicative syntax. It's the big thing that it doesn't support. There's a really nice paper on this called the F# Computation Expression Zoo by Tomas Petrusek, who's the same guy that wrote the Asynchronous Sequences library. The language spec is the definitive reference for all of those transformations. I've got a link there to the library. So any questions?